Hi everyone, this is Tairan Wang. Now I'm gonna give the behavior selection algorithms, the chapter 4 of the game AI. Yeah, and the theme is behavior select algorithms. It introduces several methods of behavior selection algorithms, including finite state machines, hierarchical finite state machines, behavior trees, utility systems, goal-oriented action planners, and the hierarchical task networks. The tutorials here, and if you are interested with this, please look the original work. The first one I want to introduce is the finite state machine. It's the most common behavior modeling algorithm. We have managed this a lot. As we know, a finite state machine breaks down an NPC's overall AI into smaller discrete pieces known as states. And each state represents a specific behavior or internal configuration, and only one state is considered active at a time. And states are connected by transitions, directed links responsible for switching to a new active state whenever certain conditions are met. For example, this is a guard. The start state is petrol, and when he uh, hear noise, he will investigate, and like that, there are states attack, investigate, and flee, and those are the transitions that the conditions to transform to another state. Like he can attack, and if the health is low, he will flee. And this is the basic structure of the finite state machine. First, we need a finite state machine, just the state. And there are some logics that when it's entered, when it's exited, we use the enter and exit, and the update function that will active each frame when it's in this state. And each state is also responsible for storing a list of finite state machine transition objects, which is for the next the class the finite state machine transition. And the first one is the valid function. Evaluates to true when the transitions conditions are met, and the get next state returns which state to transition to when valid. And the on transition function is an opportunity to execute any necessary behavioral logic when a transition fires, similar to the enter in the finite state machine state. And finally is the finite state machine. We have the initial state and the active state that's showing the first state or the current state of the finite state machine. And the update works when just for running our behavior algorithm as follows. Just the code is valid on each transition in active state dot transitions until its valid returns true or there's no more transitions. If a valid transition is found, then call the active state on exit function and set the active state to valid transition dot get next state and call the active state dot on enter function. And if a valid transition is not found, then call the active state dot on update function. There are pros and cons. The pros are it's very simple and quick to code, and it's easy to visualize. The cons is that if there are too many states, it will be difficult to install, and it is more likely to have errors as there are more states, and it's not good for reuse behaviors. It may be repetitive. And the second one I want to talk is the hierarchical finite state machine. It's a group state machine. Yeah, it's similar to the finite state machine, and it adds additional high hysteresis that isn't in a finite state machine, and it starts off in its initial state, the history state, and as the separate state is finished, it returns back to the recent state before. So like this, just the group the state is watch building, then in this state, there are childs like petrol to save and petrol to door. It returns each other, and if there's a phone ring, it just to goes to conversation and returns back to where the historical state was. So it won't have like two conversation states here. And there are pros and cons. The pros are that it provides more structural control over the layout of states, allowing larger, complex behaviors to be broken down into smaller, simpler pieces. And cons are that, similar to the FSM, cannot deal with too much states and transitions. And the third one I want to talk is the behavior trees. The behavior driven structure. The concept is that a data structure starting from some root of root node and made up of behaviors. And every behavior defines a precondition, an action specifying the actual things the agent should do when performing the behavior. Starts at the root of the tree and examines the preconditions of the behaviors, deciding on each behavior in turn. At each level of the tree, only one behavior can be selected, though its children will be examined. If a behavior's precondition doesn't return true, the algorithm skips checking any of the behavior's children and instead moves to the next sibling. Once the end of the tree is reached, the algorithm has decided on the highest priority behaviors to run. And here is the structure of the behavior tree. It firstly makes root node the current node, and when the current node exists, it runs current node's precondition, and if precondition returns true, it adds node to execute list, make the node's child current node, else it will make node's sibling current node, and then it will run all the behaviors on the execute list to choose the behavior. And the pros and cons. The pros are simple, it's stateless, since stateless don't need to remember which behavior is previously running, and it has the extensibility. It's easy to start from the base algorithm as described and start adding extra functionality. Cons are the reading time is generally greater than that of a finite state machine, and the implementation can have a large number of conditional statements and may slow in for the device due to many other factors. And the first one is the utility systems, the spool-based system, and it measures weights, combines rates, ranks, and sorts out many considerations in order to decide the preferability of potential actions. We could access how strongly we want to do certain behaviors. There may be possible actions, and either there isn't a single right to answer or the selection of a preferable action might be based on a large number of competing inputs. So just it may compare with each variables. There are many factors like the factor, the degree of want to do something or degree of need to do something. After the calculation, it has its own idea of how to deal with the goals, and it's judged by a utility-based system, suggest. And the pros are it's good for the RPG architecture, good for architectures of the system with an economic decision layer, and its preferability scores are highly dynamic so that it shows the behaviors naturally, and it's unpredictable. But if your design calls for specific behaviors are very certain moments, you must make a point to override the utility calculations with more script actions. Next is the goal-oriented action planners. It's the goal-solving mechanic. It allows an AI system to create its own approach to solving problems by being provided with a description of how the game world works, a list of actions that are possible. Objectives are typically chosen from a predetermined set of goals that an NPC may want to achieve, chosen by some methods such as the priority or state transition. The planning system can determine a sequence of actions to change the world from the original state into the state that contains the facts that need to be true to satisfy its current goals. backwards chaining research, starting with a goal you want to achieve, working out what actions are required for those to happen, then working out what needs to happen in order to achieve the preconditions of the actions you just identified, and so on. The structures is like that. First, it adds a goal to the outstanding fact list. Then for each outstanding fact, it removes this outstanding fact and find the actions that have the effect as an effect. If the precondition of the action is satisfied, it adds the action to the plan, and it works backwards to add the now supported action chain to the plan. And otherwise, uh, it will add the preconditions of the action as outstanding fact. Here are some pros and cons. It avoids a lot of authorial and directorial controls from the development team. Characters can think of for themselves. And cons is that it isn't as straightforward as with architectures such as the behavior trees, which would allow the desired behavior to be injected directly into the character's decision logic. Finally, is the hierarchical task network. It's the task-based method. Just that it aims to find a plan for a NPC to execute. HTN works by starting with the initial world state and the root tasks representing the problem we are looking to solve. This high-level task is then decomposed into smaller and smaller tasks until we end up with a plan of tasks we can execute to solve our problem. HTN is a forward planner, meaning that it will start with the current world state and work towards a desired solution. Works with a world state, it represents the state of the problem space. We have two different types of tasks, primitive tasks and compound tasks. Primitive task is an actionable thing that can be done to solve a problem. Compound tasks are higher level tasks that can be accomplished in different ways, described as methods. And the structure is like, firstly, it adds the root compound text to our decomposing list. Then for each text in our decomposing list, firstly, it removes the text. Then if the text is compound, it will find method in compound text that is satisfied with by the current world state. And if a method is found, add method's text to the decomposing list. And if not, it will restore planner to the state before the last decomposed task. If a task is primitive, apply task effects to the current world state and add tasks to the final plan list. And the pros are it's in a natural way since there's no authorial additions and it allowing a lot of reuse across different AI characters. The cons is that the user needs to build the network for HDN to work. Okay, thank you for listening. This is my presentation, and maybe my analysis is not complete or may somewhat different from the original work. So if you are interested in this chapter, please check the original work.